Last time we left off at an example right here. So what are we doing? Big picture. We're trying to be able to mathematically describe waves. Why? Because we're going to be dealing with voltage and current waves on transmission lines. So to gear up for that, we've been looking at waves in general. And we used water as our most intuitive wave. And so we looked at how we could describe a wave of water. So we had our pool that we talked about a lot the last time, and we didn't worry about the side to side in the pool, you know, because the waves, they kind of spread from side to side of the pool. But what we were saying was basically, it's the same all the way across the pool, but the waves travel down the pool. And so because they're the same side to side, we didn't worry about the side to side. And for us in a transmission line, well, it's like a linear line kind of a thing, right? And so we don't need to worry about another dimension. So when we did our equations before, we mostly dealt with X, right? X was the length down the pool or the length down the transmission line. T was our time. And when we did this example here, we switched it to Z, but it doesn't matter. We're always going to align it with one of the axes. So our transmission line is going to be aligned with one of the axes of our Cartesian coordinate system, our X, Y, Z coordinate system. And so we could kind of pick whichever one we want. It doesn't matter. We're just orienting our coordinate system in a particular way. As soon as we switch to transmission lines, really next week, we are going to pretty much always use Z. Okay. If you go on to take the follow-on course, then you won't just be limited to one spatial coordinate, but it'll be all three, because you can have waves traveling through three-dimensional space. But we are just going to deal with waves on a transmission line, so we just have to worry about the one spatial coordinate, the one distance, Z in this case, X in the previous equations. And we want to be able to specify what the amplitude is. That's the number in front of the cosine, because cos, whatever's in the brackets here inside the cos, the argument of the cosine, it's only going to vary between -1 and 1. So by having a number in front of that being multiplied by the cos, we can control it to be whatever amplitude we want. We can make it less than 1. Like if we make the A out front, instead of 10 here, if we make it 0.1, that'll get multiplied by the cos. And so the cos wave will only go between -0.1 and +0.1. We have our standard form of the equation where this is omega t, meaning all of the stuff next to t is omega. And then we could use, and we did use the last time, omega equals 2 times pi times f. And so if this is omega, we could just rearrange that equation to solve for f. Also, as part of our standard form of the equation, whatever is next to the spatial variable, in this case z, in the previous equations x, the stuff next to it, like pi divided by 15 in this case, is beta. And we have an equation for beta that is beta equals 2 pi over lambda. And so we knew what beta was. It was pi over 15. So we could just solve for lambda. So we solved the omega equation for f. We solved the beta equation for lambda. And then we could use f and lambda to figure out up. We can figure out the direction of propagation by the sign in front of the t term and the sign in front of the z term. So that's what we did. But if you notice, this wave, if you were to plot this wave, it would just carry on with an amplitude of 10 forever. So the wave would constantly be going between +10 and -10. And regardless of how far the wave went, it would still have an amplitude of 10. We got a question, Anthony, go ahead.
It's according to your inner bracket there where it says pi times 10 to the 7th.
Yep.
And you had mentioned that the, what do you call this thing?
Omega.
Oh,
Yep.
yeah, there you go. Omega. Since you also say that omega is equal to 2 pi times the frequency, you just have to put the 2 in front of that pi. Therefore, you don't have to put 2 pi times pi.
Yeah, don't get confused here, because this thing is, sorry, let me just be very precise here.
Yeah,
so let me
just trying to understand that.
Yep. That is omega. That, so omega is pi times 10 to the 7, and omega equals 2 pi f. So 2 pi f equals pi times 10 to the 7. And you could solve for f. But don't be thrown off here that it's a pi instead of a 2 pi. Whatever is next to the t is omega. Any other questions about that? All right. Well, what if you are in a lossy medium, meaning that the amplitude goes down the further it travels? We got to adjust our equation. How are we going to do it? Well, we're going to add in this guy. So if you ignore this guy just for a second, we have a cos omega t minus beta x plus phi 0. That's exactly what we had before. So the only addition here is this e to the minus alpha x. This is our factor. That's the attenuation factor. Alpha is the attenuation constant. It has units of Neper per meter. Very common on a midterm or a final exam to be asked to calculate alpha or calculate the attenuation constant. We don't have the equations to do that yet, but we're gonna next week, okay? So if you got asked that question on a midterm, let's say, find alpha, and you use an equation and you calculated it, you would need to know the units. You will lose marks if you don't put the units. If it's a multi-step question and you got to calculate this first thing and then the second thing to get the final answer, the third thing, I am only going to deduct marks if you didn't include the units for the last thing, the thing that you were actually asked for. So kind of like the first two things you calculated, if you didn't put the units, I won't dock you marks, but the thing that you're actually being asked for, you got to have the units. If you didn't put the units, it's not like you're going to get 0. You're going to get deducted something though. It depends how much. It depends on how many marks that question is worth. Maybe if it's worth 2 marks, maybe you lose, I don't know, a quarter of a mark or half a mark or something like that. Okay. So you'll lose something. So make sure you know your units. You can put them on your cheat sheet if you want to. Okay. So we've got this extra term. How does it work? How does it control the amplitude? How does it model a wave that is decreasing in amplitude the further it goes? So here's a nice picture. So this blue wave, clearly you can see it's oscillating like a regular sinusoid. And if you look at the period, it's 1.5, right? Sorry, it's 2, right? Peak to peak is 2, to the next peak is 4, to the next peak is 6, to the next peak is 8. So it's just a regular old sinusoid, but the further we go in x, note our x-axis here, we're not dealing with time, we're just dealing with distance. So if you wanted to look up to the generic equation up here, you can consider it to be at time t equals 0. Okay, if it was time t equals 0, it's like we've taken a photograph, we've taken a picture, like our wave pool, wipes out that term. Okay, so we're only looking at y at x. We peak here, right? We peak at 0. At x equals 0, we are at the peak, which means we don't have a phi 0. So basically, compared to our equation up here, that one's gone to 0 because we're just thinking about it as at t equals 0. That one's gone to 0 because we have a cos and cos with no phase shift peaks at 0, right? Because at x equals 0, that thing's gone as well. And so the cos of 0 is 1. Then 1's going to get multiplied by the a, which is 10. That's why we're up to 10. X, so let's consider that. Let's go through this in a little detail here. Let's say we're at x equals 0. What do we got? Well, if you look up top here, we're considering a time t equals 0, so that's gone. X equals 0, that's gone. And we rationalize that phi 0 has to equal 0. The only way that we could do that is by the peak here, right? We could also look at the equation. We're given the equation, but I'm trying to relate it back to the generic one that we've been looking at. Okay, x equals 0, right? That means all the x's equal 0. That x equals 0, that x equals 0. So we have minus alpha times 0. So that's e to the 0. E to the 0 is 1. We just have a. Okay, now let's look down here at the specific equation. X equals 0. All right, we have pi times 0. Well, that's 0. The cos of 0, that's 1. So we can forget about this one. Here is x. X is 0. Minus 0.2 times 0 is 0. E to the power of 0 is 1. 1 times 10 is 10. Boom. That's why we're there at x equals 0. Okay. Let's take another point. Let's take x equals 2. We plug in 2. We have 2 pi. The cos of 2 pi, that's 1. If you weren't sure of that, you could punch in your calculator. Just make sure you're in radian mode. 2 pi is 360 degrees. So it's the same as the cos of 0 because it's done a full rotation, a full cycle. So 2 for x, 2 pi, cos of 2 pi is 1. Ooh, we got to plug in x here now, though. X is 2. Minus 0.2 times 2. So that's minus 0.4. E to the minus 0.4. So you got to get your calculator. You go E
It's
minus
670
0.4.
milli.
0.67, right? So like Anthony said, 0.67, then you multiply it by 10, right? So you get 6.7, meaning that at 2, this would be 6.7. All right, let's take it all the way out. 8. All right, plug in 8. 8 pi. Well, that's just going to be 1 as well, right? Punch in your calculator if you don't believe me. So you got to plug in 8 there. Minus 0.2 times 8. Minus 1.6. E to the minus 1.6 is 0.20189, blah, blah, blah. Then we'd have to multiply that by 10. So we get something very close to 2. It doesn't work just at the peaks. It also works everywhere else. So you could choose, x equals 1. X equals 1, you'd plug in the 1 there, you'd have the cos of pi. The cos of pi is minus 1. So that's where you'd get the minus, because we're down below, right? And then you'd plug in 1 for x there. So you'd have to do e to the minus 0.2 times 1. And then you'd multiply that by 10, and you'd get this value down here. The further it travels, in other words, the greater x is, the bigger that number is. So the bigger the negative number is in the exponential, and exponentials blow up quickly or go down really quickly if they're negative. So bigger x, the smaller the attenuation factor, which gets multiplied by our amplitude A. And so that's why you see it getting smaller and smaller and smaller with x. The peaks are defined by this, because remember, the cos is just bounded between -1 and 1. So if we're looking at the positive side, the biggest it can be, the highest it can be, well, cos, the highest it can be is 1. And so it's just going to be dictated by the term out front, 10e to the minus alpha x, or ae to the minus alpha x, right? In this case, 10e to the minus 0.2x. So that's what's called the envelope. It's bounded on top and bottom by this envelope, which is the part outside of the cos function, which is that ae to the minus alpha x. So let's do an example of that. An electromagnetic wave is propagating in the z direction. All right, we're in the z, we're not in the x, but whatever, doesn't matter. It's in a lossy medium, and it's telling us the attenuation constant. You see how it says an attenuation constant alpha equals 0.5 meter per meter? Sometimes I won't be that kind on an exam. In the question, I might just say, the attenuation constant is 0.5 meter per meter. And the reason I do that is because if I give you the letter, then people may just go equation hunting, right? You're just looking at your equations. Oh, there's an alpha given. What equations have alpha in it, right? And you're like, okay, you've narrowed it down to these equations that have alpha in it. And then what else do I have? Okay, I have this other thing. Which of those, 3 equations, let's say, have an alpha in it? Oh, okay, but I'm given something else and only one of those equations has that in it, so I'll use that equation without any understanding, okay? Not even knowing what alpha's name is. So sometimes I might just say alpha equals something. Sometimes I might say the attenuation constant equals something. Sometimes I'll be nice like this and say both the attenuation constant and give you the commonly used symbol, but don't count on that, okay? If the wave's electric field amplitude is 100 volts per meter at z equals 0, how far can the wave travel before its amplitude will have been reduced to 10 volts per meter? Let's break this down a little bit. The amplitude is 100 at z equals 0. Let's think about it in terms of this one, because we were talking about this one. We got a nice picture. Imagine the question instead said, if we were to convert the question to be appropriate for this picture and this equation, it would be the wave's amplitude at x equals 0 is 10. So imagine this equation was not given, but you were told that the wave's amplitude at x equals 0 is 10. You say, well, what is that telling you? Like, what part of the equation is it giving you by telling you the amplitude at x equals 0, or in our case, z equals 0? Any guesses?
Would it be that omega t also goes to 0?
Okay, so the omega t is actually an interesting one for this example because it doesn't talk about frequency at all. So that's maybe why you're thinking like, maybe omega t also goes to 0. And you can think about it that way if you want to, but you can even do more than that. Because in this case, they're giving us an amplitude here, and they're asking us how far the wave can travel before the amplitude equals something. In other words, we're only interested in amplitude. If we're only interested in amplitude, all we care about is this wave envelope, right? All we care about is the part in front of the cos. Everything inside the cos is just making it go between 1 and -1. Everything that's determining, what the wave amplitude is at 6, what the wave amplitude is at 4, what the wave amplitude is at 5, that's determined by the stuff in front of the cos. So we don't have to worry about the omega t. Any other thoughts on what telling you the amplitude at x or z equals 0 is telling you in terms of that equation in the top right? Think about it in terms of this one here. If you were not given that equation, but you were told the amplitude at x equals 0 is 10. Which part of the equation are you being given? You're being given this part, right? Or another way to think about that is you're being told what it is at x equals 0, right? So we said we only really care about this part because we only care about the amplitudes. If x equals 0, that's e to the 0, that's 1. You're being given a. So really what we're being told by this statement right there is a equals 100. We're also given alpha, so I'll write it down. All right, so what do we know here? Well, we know our wave amplitude is going to be given by this thing, and we don't need to worry about the cos because, yeah, we're being typed it in the chat there. A equals 10 for this case, but for our case, it equals 100 initially, but it's reduced to 10. So we need to know, like, at what point is it reduced to 10? In terms of this, do you remember how we calculated like it was about 2 here? It's kind of like you were asked this question. You weren't given that equation, and you were told the amplitude at x equals 0 is 10. What is the amplitude at x equals 8? Okay. That's kind of the equivalent here. So we can just come up with a little equation here and go a, I'll write it like this, a e to the minus alpha, we're dealing with z's, equals, I'll say 10, right? Because we want to know when it equals 10, and we know a, so it's 100, and we know alpha. This is the whole question. If you can write this equation, the rest is easy because we're solving for z. So let's talk about how we can write this equation. Anybody have any questions about that? So what we really have is a, which we determined from this statement up here saying what the amplitude is at z equals 0. We're only interested in amplitude. That's why we're only interested in envelope. Amplitude is max, okay? It's the maximum. So that's why we're only interested in these points. The wave amplitude determines those points. The wave amplitude is given by this, or more generically by a e to the minus alpha x. In our case, we're using z instead of x, so we just swap that out. We're told alpha in the question. And we were told a by giving us the value at 0. And we want to be able to figure out what the value of z is at the point where the amplitude equals 10. So here we just have to solve this. So really the whole challenge to this question is coming up with this equation. After that, what do? You divide, you bring the 100 over, right? So you'd have e to the minus 0.5 z equals 10 divided by 100, which is 0.1. You got to get rid of that e. So we got to take the natural logarithm of each side because the ln of e will cancel out. And it'll just bring it down to 0.5 z equals the natural logarithm of 0.1, which you'd have to use your calculator for probably, unless you're good with lns. I'm not, so I get that it's minus 2.3. So let me just rewrite this here. Minus 0.5 z equals minus 2.3. So we just solve that for z. Okay, so it's going to be 4.6 meters. So all of this was that equation, right? The rest is just it's kind of a basic math problem. But let's say you weren't confident in your answer. You could plug this into there and see if it does indeed equal 10. If it doesn't equal 10, If you plug in 4.6 for Z and it does not equal 10, you've made a mistake. Rubina says, why don't we have the cosine part? So that's what we were talking about before, about how the only reason why is because the question is only concerned with amplitude. And the amplitude is completely determined by the part in front of the cosine. Because cosine just makes it oscillate between 0 and 1, or sorry, between 1 and -1, right? Just oscillating between -1 and 1. So it is not determining the amplitude. The amplitude is completely determined by a e to the minus alpha x. And because the question is only concerned about amplitude, we don't need to worry about the cosine. So let's say we wanted to double check our answer, right? So we'd go minus 0.5 times 4.6, which was our answer. That gives me minus 2.3. Then I would need to do the exponential of minus 2.3. Then I would need to multiply that by 100, and I get 10.0259. Very, very close to 10. The reason why it's not exactly 10, because that's rounded a little bit. Okay. Any questions about this one?
I do.
Yeah.
So if you were to figure out a different amplitude on a different exposition, and only for the amplitude, going back to our waveform there.
Yep.
Yeah, let's just say, for example, 6.
Yep.
And so therefore it's the same method. You don't have to include the cosine because
be
we don't care
exactly
about
the same.
oscillation. We just care about the amplitude.
Yeah. So basically it would be the same. You would need to be, what did the question say again? It said, how far can it travel before it reaches a certain level? So basically you're being told like some level over here, like maybe that's like 4. Let's say it's 4, okay? So in this case, you'd go 10 e to the minus 0.2x equals 4, and you'd solve for x. And it looks like that would be somewhere in the neighborhood of, I don't know, somewhere around 5, like 5 or a little below 5, a little above 5, something like that. You'd have to actually do the calculation to figure out exactly what it is.
Okay.
But it would be, if you were asked to find where, in terms of x, the amplitude equals 4, you could go the other way, right? And you could say, what is the amplitude at x equals 6? In that case, though, you just plug 6 into the x and see what it equals. Any other questions? Okay, all right, moving on. Complex numbers. We're going to do lots of complex numbers. I know you've seen complex numbers before. We're just going to review them. Okay. We are going to write complex numbers in 2 different ways, and we're going to flip back and forth. Anthony doesn't like them. Hopefully you'll learn to love them because we're going to use them a lot. So we got complex numbers. What's a complex number? Well, it's a real part, an imaginary part. That's one way you can think about it. That's when it's in rectangular form. So here's how a complex number z would be written in rectangular form. X is the real part plus j times the imaginary part y. J, square root of -1. In your math classes, you probably used I for the imaginary number. We're electrical engineers, so you probably saw in earlier classes that we use j instead because I is so often used to represent current. Anthony, is that another question or from last time?
Sorry, forgot to lower my hand.
Nope, no problem. I just wasn't sure. Okay, this is the rectangular form. Real number plus j times imaginary number. Real of z is x, imaginary part of z is y. You don't include the j. The stuff next to the j is the imaginary stuff. We could also write them in polar form. So in the complex plane, which means the x-axis is the real part and the y-axis is the imaginary part, you'd have some point. That point would have some x, would have some y. You could also write that as a vector, let's say, that has some length, the magnitude of z, and it's got some angle, theta. They're the same thing. It represents the same point. Just two ways of representing the same thing. Some calculations we do will be easier in the one form and others will be easier in the other form, and we'll be flipping back and forth like crazy. If it's in polar form, we have a magnitude. These vertical lines, that means the magnitude or length of z. We could write the angle as e to the j theta, or we could just use this angle sign. They mean the same thing. You can use either one. E to the j theta. Let's think about Euler's identity. E to the j theta, cos theta plus j sine theta. So if we looked at this form here, the magnitude of z times e to the j theta, well, if we use Euler's identity, that means we would just multiply through the magnitude of z, right? So we have magnitude of z cos theta plus j magnitude of z sine theta, okay? Where do those come from? Well, if you think of magnitude of z times cos theta, magnitude of z times cos theta, if you used your like SOHCAHTOA rules, what you'd find is magnitude of z times the cos of theta, that is x. That's that side, okay? That adjacent side. And if you did magnitude of z times the sine of theta, and you did a different right triangle with your SOHCAHTOA rules, you'd find that this line, this vertical line going up the y-axis, well, that would be magnitude of z times the sine of theta. That's where that comes from. So we can always get the rectangular form. If we know the magnitude and the angle, we can get x. We can get y, so we can get the rectangular form. If we have the rectangular form and we want to go to the polar form, we can get the magnitude by using essentially just the Pythagorean theorem, right? X squared plus y squared square rooted. That's that one. The plus sign is because magnitudes are always going to be positives. It's like a length, and square roots have a plus minus sign. But we don't want the minus sign because it's a magnitude. It can't be negative. And the angle, well, that's just going to be the inverse tangent of y divided by x, the imaginary part divided by the real part. But we have to be a little careful. Because if we think about our quadrants, our calculator might lie to us. Because imagine for a second you're in quadrant 3. That's where both the x part is negative and the y part is negative. So if you plugged in, if y was like -2, let's say, and x was -3, well, the minuses are going to cancel out. And your calculator is going to tell you the inverse tangent of -2 divided by -3. That's a positive number, which would be the same as if it was in the quadrant 1. And they were both positive. Now you might have a smart calculator. Know what your calculator does. Because maybe your calculator doesn't just go, oh, I have a negative divided by a negative, so that's a positive. Maybe your calculator realizes that, oh, I have a negative, imaginary part and a negative real part. And so I'm going to adjust it to the right coordinate. Basically, you just need to pay attention to this so that you know if you need to add 180 to it to get in the right coordinate. We're going to do an example later of this, but just something to be paranoid about. Always ask yourself what coordinate you're in for the angle. So here's a better picture, the same one I drew, but just a little more clear. We have the equations we just saw. The only additional thing on this slide that we haven't seen before is this asterisk. That is the complex conjugate. Really easy. All you got to do is you flip the sign of the imaginary part. Here it's plus. If we have a complex conjugate, nothing happens to the real part, but whatever the imaginary part is, you flip the sign. If that was minus, then that would be plus. This is rectangular form. If you're in polar form, it's just as easy. You just flip the sign of the angle. So that is negative. Negative. Another way to get the magnitude is to multiply the complex number by its complex conjugate, then take the square root. But we'll normally use like the Pythagorean theorem kind of way. If this has been a little while, if you're a little fuzzy on this stuff, if you need a little practice, you can look through this example in the text. Example 1.3, it should ring some bells with, I think, 240. Either example 1.3 or 1.4 in the text is like a 240 style problem. One thing I'll just point out now, while I'm kind of, recommending you go through this example, in general, when you are working on the problems, make sure you're not just looking over the solution. I recommend you do it. So for example, if you went to example 1.3 here, I would recommend you get like a piece of paper and you cover up the solution. You can just read the question and you try to solve it yourself. If you're really stuck, look at the next line, right? Maybe you just needed the equation, all right, but then cover it back up, use the equation, actually write it out yourself, actually punch it into your calculator yourself and see if you get the right answer, and do that for each step. I think a trap that a lot of students fall into is you just look over the solutions and you're like, okay, I see how they went from there to there, and all right, I guess I kind of see how they went from there to there. And then if you get to there, okay, then you just plug the numbers into there and you get that number, right? And next thing you know, you're on a midterm or final exam. And now you're really on your own, right? And maybe the question is slightly different. And you haven't had to think as deeply about it because you just kind of went, okay, I'm going from there to there and then from there to there. But if you aren't given that and you have to really think deeper about it, like what equation should I use? Why should I use that equation? If you have to think deeper about that, then you'll be much more prepared to handle a twist in the question, a slightly different question than what you've seen before. So make sure you're doing it yourself. Also plugging the numbers into your calculator yourself. I highly recommend you bring a calculator to all of our classes because we'll do lots of examples and I recommend you punch the numbers in. Why? Because you would not believe the number of calculator mistakes that happen on midterms and finals. It just costs marks. And you got to think if you did more practice with it, it would become more like second nature and you'd be less likely to lose those marks to make those mistakes. Okay.
Will we be able to use your slides on the exams?
So you are going to create your own cheat sheet and you are allowed to use my slides. You can use whatever you want. I'm not going to limit you. You could use pieces from the text. You could use, what pieces from the slides. You can use whatever you want to. The only limitation is just you have to be able to see it with your own eyes. There are no magnifying glasses or anything like that. You can write it by hand. You can create it on the computer. It's up to you. Okay.
Thank you. No magnifying glasses.
That's right. Just no magnifying glass. All right. Phasors. If you hated complex numbers, and you probably really hate phasors. Maybe phasors are like a blur from 240 or something like that. The sad news is that we're going to use phasors a lot, but we're going to use them in one particular way. And so if you get kind of the basics of it down, it's just going to be much the same thing over and over and over and over again. What's a phasor? Well, if you are dealing with sinusoids, like we are exclusively, then you can use this phasor representation, okay? Now, you can look at the table on the right here, and you'll see how you write time domain version versus the phasor version. So, what does all this mean? Well, best way to think about it is, well, let's start with the simplest one here. A cos omega t. All right, A cos omega t. Let's think about that one for a second. Let's come back here and look at our friend Euler. Let's say theta equal to omega t, just for fun. All right, we would have, because theta is just a generic thing. It could be x, could be theta, whatever variable you want to represent it here, but we're using x for something different. We're using it for the real part. So we're not going to use x, we use theta. But this is a generic equation, right? So e to the whatever, e to the j whatever equals cos whatever plus j sine whatever. Here it equals omega t. So if we did e to the j omega t, well, using Euler's identity, that would be cos omega t plus j sine omega t. What if we multiplied it by a? Well, if we multiplied the left side by a, we have to multiply the right side by a. And then we could say, well, what if we took the real part of it? So it was the real part of a e to the j omega t. So don't worry about why you might do this yet. Just follow along like what the path I'm taking here. If you were asked for the real part of this thing, which is equal to this thing, well, you ignore the imaginary part. So you ignore that part. And you would just have a cos omega t. Okay, so then you might think, well, that kind of looks like a phasor sort of a thing. But then if you come to our table here, a cos omega t in the phasor domain is just a. Okay, let's look at this bullet here. E to the j omega t is not usually written. It's there, we just don't write it. Why don't we write it? That seems kind of irresponsible. That's an important part, right? That's where the omega t comes from. It's because it's assumed, it's in everything. Well, all the waves we're dealing with vary with cos omega t. Every equation would have a cos omega t in it. So every equation in the phasor domain would have an e to the j omega t in it. So we have to write it over and over and over and over again. When it's always there, it's always assumed. So we just don't write it when we're in the phasor domain. That's all. So it's always there, we just don't write it. That's why there's no e to the j omega t there. It's implied, it's assumed. So coming back here for a second, when we did all this stuff with the Euler's identity and then we took the real part, well, this is going to be similar to what we do when we convert from the phasor domain to the time domain. So let's take an example here. This is our equation at the bottom. This is our phasor form. That's the right-hand side of this table. If ever we want to convert from the phasor domain to the time domain, well, I said in the phasor domain, we were ignoring the e to the j omega t, right? But it's actually there. So if it's actually there, when it comes time to convert to the time domain, we need to pull it out, right? We need to explicitly include it because when we're in the phasor domain, we don't write it. We don't include it. That's why we multiply by e to the j omega t. Then we take the real part. So this might still seem a little fuzzy. So let's take the one that we spent all last class working on. That one. That was before we added in the loss term in this class. So let's assume that that's right. If that's right, the phasor form z tilde on the right-hand side here, a e to the j beta x plus phi 0. If that is true, I should be able to apply this equation at the bottom and end up with that. So let's go through that as a way of kind of convincing you that it is the case and to give you a little bit of a feel for how this works. Okay. Let's do it. So I am assuming it's correct. Z tilde equals A e to the j beta x plus phi 0. And I'm going to use the equation in the bottom to convert it to the time domain. What's the first thing we have to do? We have to multiply it by e to the j omega t. So z tilde times e to the j omega t equals our z tilde, which is a e to the j beta x plus phi 0 times e to the j omega t. Because they have the same base, they're both e, they're both the exponential, we can add the powers together. They both got a j in them, right? So we can factor out that j and put the rest in the brackets. So we can just do equals a e to the j omega t plus beta x plus phi 0. Any questions about that so far? So all we did was we assumed the phasor's right. We took that phasor, we multiplied it by e to the j omega t, and then we, because they had the same base, we could combine the exponents. And we factored out the j of both of them because they both have a j in them. Okay. Now let's use Euler's identity. So we have a e to the j omega t plus beta x plus phi 0. Now remember Euler's identity. It's it's cos of whatever's up there plus j times the sine of whatever's up there. And we got the a out front, right? So we'll do a cos of whatever's up there, whatever's next to the j, omega t plus beta x plus phi 0. But Euler's identity says there's plus j a sine omega t plus beta x plus phi 0. So all of this still is just z tilde e to the j omega t, right? We started there, we multiplied them together, we combined the exponents, then we used Euler's identity. And what's the last thing we have to do? We have to take the real part. If we take the real part, the entire imaginary part goes away. So what are we left with? A cos omega t plus beta x plus phi 0. You might be thinking, why on earth would you want to do this? Okay, it's going to make life easier. This makes it a little trickier, but ultimately to make it easier, including things like differentiation in the time domain, you just multiply by j omega. Integration in the time domain, you just divide by j omega. Where does that come from? Well, imagine you were taking the derivative with respect to time of some phasor, okay, some phasor. Remember that every phasor, actually, there really is an e to the j omega t. We just don't write it. But if we take a derivative, we have to worry about it because there's a t in e to the j omega t. So if we're taking the derivative with respect to t, we have to kind of, you know how we say it, it's implied but not written? Well, we need to worry about it if we're taking a derivative. And so what would the derivative of this be? Well, whatever's next to the t comes out front. J omega, and then you have e to the j omega t. But we're still in phasor land, so we don't write the e to the j omega t. We just have j omega. That's where that comes from. Bottom line here is it makes some operations easier. It makes manipulation mathematically easier. Certain things are easier to see in the phasor domain. So if there's calculations that are easier, it's easier once you get used to it to get intuition about it. but I want you to really, because from this point forward almost, we're no longer going to write the waves in terms of coses. We're going to use the phasor domain. So if you see something like that in your head, what I want you to think is when you see the e to the j something, you know, it's got like a beta x up there, maybe some angle. I want you to think, oh, that's just a wave. That's just like the thing that we were talking about in the pool. That's, you know, got a cos, omega t plus beta x. You can get, like, I feel like this is the first place in ECE 370 where the train can start to go off the tracks, because we're going to start representing things like this. And then if you don't have that nicely tied together in your mind to just the regular old cosine wave equation, then we just build upon it and build upon it and build upon it. And you kind of like lose that connection to everything we talked about last class with like these physical waves and what things mean, okay? So this is what we just went through in some detail, right? We just went through this one. In fact, we even had it more complicated because we included the phi zero. This one's without the phi zero. Cos omega t. That's why really in hiding here, there isn't e to the j omega t, but we just don't write it. Just the convention. So a cos omega t plus beta x is just a e j beta x. We can tell what direction it's traveling in. How do we know? Well, if we're in the time domain, we look at the signs in front of the omega t term and the beta x term. If they are the same, means it's traveling in the negative direction. If they are different, means they're traveling in the positive direction. In the phasor domain, we always have an e to the positive j omega t. That's our convention. When we don't write it in the phasor land, it is an e to the positive j omega t, meaning that that one is always positive when we're in the phasor world. Okay, when you're in the time domain, it could be positive, it could be negative. But here, it's always positive, which means the sign is completely determined by what's in front of the e to the j beta x term, because that sign comes from that sign, okay? So it's kind of like the omega t sign here is always positive, and so it's going to be completely determined by the beta x. So because the e to the j omega t is positive, and in this case, it's positive e to the positive j beta x, the signs are the same. When they're the same, traveling in the negative x direction. If it's negative, now they're different because we have a negative there, but there's a positive in the e to the j omega t. So they're different. That means it's traveling in the positive x direction. So now it's kind of even easier than it was before to determine the direction a wave is traveling in. Is it positive or is it negative? That's all. And it's opposite. So if it's positive, traveling in the negative x direction. If it's negative, traveling in the positive x direction. Example 1.4, another good one to go through in the text to kind of get you used to, kind of fired up and review this kind of stuff. And that is the end of chapter 1 and kind of our basics of waves. And now we're going to get into the good stuff. All right, the real stuff that you're actually going to be tested on in that. All of that was kind of foundational. We are in chapter 2. We are going to stay in chapter 2 for the rest of this first part of the course. Okay, we're going to take our time in chapter 2. So this is only 8 pages. I'm not asking for a lot. Like, you're not reading a novel here before each class. It's not that many pages, but it's fairly dense, and you may have to read it over and over and kind of look back to earlier stuff and that sort of thing. Okay. I've been going on and on about transmission lines since our first class, like probably in the first 5 minutes of our first class. When I'm going through the syllabus and stuff like that, I talked about transmission lines. And this whole first part of the course can be summed up as transmission lines. So finally, we can talk about what is a transmission line. So in your head, when I say the words transmission lines, what do you think about?
Usually it's going to be the power transfer lines, but you've
Yeah.
said those aren't it.
Well, if we think very generally, if I want a very, very general definition of transmission lines, then for now, we're going to have a specific definition for our class of something specifically called transmission line effects. Okay.
I
But
think
here
the-
we're just talking generally. So any other ideas? So that one I'm going to include power transmission lines. Anthony, do you have another one?
yeah, I just think of transmission line as a pathway for communication.
Yes.
From point A to point B.
Yeah. Yeah. So that is definitely a pretty generic one. And Eduardo in the chat has even gone in another direction. Not wrong. We didn't say anything about electrical stuff. Could be a pipeline. You could think about that as a transmission line. You're transmitting something. So if you want it to be really general, you could say it's any structure or medium that is transferring one thing to another. Okay, or something from one point to another. If you want to be a little more specific for electrical engineering, you could say some kind of structure or media that is transferring energy or information. So that kind of covers both of the earlier comments about power lines and communication stuff, energy or information. And a little more relevant to our class, we're going to look at transmission lines that are guiding electromagnetic signals or electromagnetic waves. Okay. That's still pretty general. Could represent lots of stuff. We're going to see some of the things that we're talking about for this class. And we're going to talk about when are these transmission lines important as far as electromagnetics are concerned, and when are they negligible? But before we get there, that's the middle chunk of this diagram. What about the chunk at the left? Like it just says generator circuit. What are some ideas? So that's like an AC source and a resistor, but generally more general than that, an impedance, a generator impedance. What could that represent, do you think? Any ideas? I think the most obvious one is when you're in the lab, like your circuits lab, and you've got the signal generator on the bench. Right.
Yeah, I think of it like, let's say you have low impedance on one side, and the reason why you need, and correct me if I'm wrong, of course, and the only reason why you need low impedance on one side, so that way you have the max transfer of energy to the other side.
Okay.
But I could be wrong.
No. That's getting specific, but we are going to be dealing with that. That's important. If you did your 240 labs, you might remember that, how you had to take into account that maybe the impedance of the signal generator was, it could have been set to 50 ohms, or maybe it was set to high Z, and based on its setting, the amplitude of the waveform would be different. That might ring some bells to you. Let's not get quite that specific yet. I'm going to keep it a little more general and just say, oh, it's just a sinusoidal voltage source. It's got some impedance. So it could be that signal generator on the bench. You turn it on, you hit the power button, you say, I want a sine wave, maybe. You say, I want it to be at this frequency. And I say, I want it to be at this amplitude. All right, that could be a generator circuit. You could go to the next level and say, well, what's really going on inside of that signal generator? And if you cracked open the case and you wouldn't want to do this, you'd upset the lab managers and people, you're probably your lab instructor, but you would see a printed circuit, maybe more than one printed circuit board in there. You'd see a bunch of components soldered to it. And some of those components would make this oscillator, right? It might be a phase lock loop, it might be some oscillator circuits. If you go on to take 440, you probably learn how to design some oscillator circuits using op amps or transistors or capacitors, resistors, some combination of these things, inductors. If you just design that circuit, well, that's also kind of a voltage, sinusoidal voltage generator circuit. So that could be represented by this. What if you thought about your cell phone that's sitting on your desk probably, or in your pocket or something? You'd be like, how could that represent a generator circuit? Well, they could represent it in a lot of different ways. First of all, there's oscillators in there. So it could be the exact example I just gave. Another one, it's sending, even though you can't see it, the base station nearby and your Wi-Fi base station too, your Wi-Fi router, are both sending electromagnetic waves to your phone. Even if you're not doing anything with it, it's communicating with them, right? It's knowing what one it's connected to and what the strength is. And, you know, it has to be, because if you get a notification that pops up on your phone, it's like the phone only knew to pop up that notification because it got notified from the base station by sending an electromagnetic wave. So an electromagnetic wave is sent from the base station. It impinges upon your phone. It like kind of goes through your phone, but the electromagnetic energy that's impinging upon the antenna that's inside your cell phone, that induces a voltage and current on the antenna. And that's going to be sinusoidal in some way. It will be modulated, but don't worry about that. It could be viewed as the generator. If you took that abstract view and you're just like, I know there's an antenna, I'm worried about the stuff after the antenna. I just know that the antenna is like, it's like a source, it's like a voltage source of, you know, a voltage source, a sinusoidal voltage source. So you can kind of like abstract it away, right? It could also be an earlier circuit. It could be like a previous stage amplifier, any circuit. And you're just like, you know, I know coming from that previous circuit, whatever it is, it's sinusoidal voltage. It's going to have some amplitude. It's going to have some impedance, like looking back into, say, that amplifier or something like that. That's like the ZG. It could be like your generating station for a power, your, you know, power transmission, right? It could be in, it could be many, many things. What about the other end, the load on the far right? Any ideas? What could that be? One thing it could be is a resistor. That's a pretty boring thing for it to be. Like it could be, you know, literally just a resistor. It could be, Anthony, got one? Emerson, anyone?
Could it also be
Yeah.
the phone like you mentioned earlier? Like,
Okay, I like it. Yep, I'll talk about that in a second. Anthony, you got one?
Yeah, that could be another thing, like a printer. Anything that would
Absolutely.
communicate with or take up a voltage, whatever you're going to use it for.
Yeah, a printer, a blender, a toaster, a light bulb, right? All the lines coming from, if we're thinking about power stuff, you got some, you know, lines coming into your house. It goes through your walls to the outlets. You plug something in the outlets. And so all of those lines would be considered the transmission line. And then the thing, whether it's a light bulb or a blender or a printer, that you could model as the load, okay, the ZL. The other thing that was said was maybe your phone could be like the load as well. And yeah, so in many different ways. To take like the antenna example, the antenna, not only could it be the generator, could you view it as a generator, you could view it as the load, but you'd have to think about it more as a transmitting. So let's say you want to send the signal to the base station and it's connected to an antenna. Well, the antenna has some input impedance that would be represented by ZL. And the power that would get dissipated in that resistor as it's shown here is actually the power that's being sent wirelessly. So in that case, it's acting like the load. It could also just be the next circuit, like maybe whatever you're doing with your transmission line and stuff, it's just connecting to some amplifier. That amplifier has some input impedance, ZL. That can represent the load circuit. So if you just look at this diagram, you might think, well, this is a simplistic kind of useless diagram, because like generator, is that like a signal generator, and then it's transmission line just like kind of a piece of wire, and then are we connecting that piece of wire just to like a resistor? This is kind of so simple that it's useless, but in fact, it's so generic that it can apply to so many different things. So we can abstract it away into these three chunks, and we're going to focus on the transmission line chunk of it. And we're going to study like 4 or 5 different very specific types of transmission lines. So whenever you see this diagram, think in your head like the generator circuit could represent a ton of stuff. The load circuit could represent a ton of stuff, and the transmission line could be a ton of different types of transmission lines. And we'll look at a few specific ones. So the big question though is, how come you didn't pay attention to these things in 240 and 340? For instance, when you were in your circuits lab, whenever you've hopefully had some kind of a circuits lab in person at this point, I'm hoping that you haven't had it all online. That'd be a little disappointing, but you'll catch up. If you did, don't feel bad about it. We're back in person now. It'll be maybe a rough first couple of weeks, but then you'll catch up to everyone. So don't feel too bad about it. But if you did have it in person, and you're doing like a breadboard lab in 240 or something like that, your basic circuits class, if you didn't take it at CSUN, and you've got some components, maybe you got some op amps or resistors or something like that in the breadboard, and you need to connect one pin to another, right? You go over to the wire spool, the spool of wire, you get your wire cutter, you just snip it off, you strip the ends of it, you stick it in. You probably didn't give any more thought to the length of the wire than just like, well, I don't want it like to be like ridiculous looping all over. I need it to be long enough. Maybe you were picky and you were like, I want my breadboard to look nice and neat, so I'm going to cut it the right length so that it perfectly fits between this hole in the breadboard and that hole, right? But you never thought about, is it going to affect the performance? Is it going to make things work or not work? No, you just plugged it in and it was fine. And we're going to see that, in general, for our stuff, you definitely couldn't do that. It could totally screw everything up. And so then the question is, how do you know when you have to worry about it, when you can ignore it? And the answer is, well, it depends on a couple things. Depends on 2 things: the length of the line. We're calling that L, physical length. You get your ruler and you measure how long this thing is in meters. And the frequency. One isn't enough. You can't just be told the frequency and know if you need to take transmission line effects into account. You can't just be told the physical length of the line and know if you need to. You have to know both. And rather than F, we're normally going to think about it in terms of wavelength. How do you calculate wavelength? That's lambda, wavelength, UP divided by F.
Question.
Yeah.
It may sound a little bold, but do you think the shorter the line on a board, or maybe a shorter trace, but whatever it is, the shorter the better? Is that a little bold to say?
No, I'm going to say no. The only reason why you'd want it to be longer is, well, it would be, so things could couple a little easier if they're really, really close to each other on a board. And you might get things so close that you could have problems with like having it difficult if you're soldering it by hand or something like that. But generally, shorter is going to make the transmission line effects less predominant. However, what we're going to find, like many, many things in engineering, you try to take advantage of these things. So in some cases, like if you're trying to eliminate or minimize transmission line effects, then it's pretty much like you're going to try to make it as short as possible. But what we're going to find is we're going to take advantage of them. So we're going to make them a certain length so that we get certain advantageous properties of them.
Okay, I only brought that up because of communication lines, like say from whatever digital circuitry to a processor,
Yeah.
and in between is
Yep.
these lines, and the sole purpose was to prevent crosstalk.
Yeah. So crosstalk is a big thing you got to worry about. So you don't want lines like too close to each other or running parallel with each other for a long time. And so short is better, but you also want separation between two lines that could couple to each other. But we're going to find we can do all kinds of fancy things by making the lines particular lengths and taking advantage of these things I'm calling transmission line effects. Okay.
That's why I'm here.
Yep. So just to finish off, lambda and f are just inversely related. So instead of saying that it depends on the length of the line and frequency, I could have just as equivalently said, it depends on the length of the line L and the wavelength lambda. And specifically what we're going to look at is the ratio of L to lambda, which is nice because they have the same units. L is the physical length of the line. Lambda, that's going to be in like meters. Lambda is the wavelength in meters. So it's a nice fraction that doesn't have units. And based on this value, which we're going to do some examples of next time, we'll know how serious these effects are. And next time we're also going to talk about like, what am I even talking about? Like what effects, what problems could this cause? We'll start to talk about that more next time. So this is where we'll pick things up. We're going to take a specific example where we have some voltage source. We've connected a transmission line to it that's L long, and we've connected some load to it on the other end. And we want to think like, what's going to happen here? Like, what's happening at AA prime versus what's happening at VBB prime at a particular point in time. So that's where we'll pick things up next time. Any final questions before I close it off?
Just I figured my question I had for you.
Oh, okay. I'll stick around for you. Anyone else have anything before we go? Okay. Have a good night. Have a good weekend. I'm going to stay here. I won't close it off, but
Good night.
I will see you Monday.